Hello students, here we start a solid state chapter from physical chemistry. Introduction. As studied earlier, the solid state of matter is characterized by strong interparticle forces of attraction. As a result, most solids have definite shape and volume, which change only slightly with change in temperature and pressure. The smallest constituent particles of various solids are atoms, ions, or molecules. All such smallest constituent particles of solids will be referred to as particles in this chapter. Now we will see types of solids. There are two types of solids, namely crystalline solids and amorphous solids. So characteristics of each one we will see one by one. First, crystalline solids. Study of many crystalline solids indicates that they possess the following characteristic properties. First one, there is a regularity and periodicity in the arrangement of constituent particles in the crystalline solids. The ordered arrangement of particles extends over a long range. Second one, crystalline solids have sharp melting points, that is, they melt at a definite temperature. Third, all crystalline substances except those having cubic structure are anisotropic. In other words, their properties like refractive index, thermal and electrical conductivity, etc. are different in different directions. For example, ice, salts such as NaCl, metals such as sodium, gold, copper, and materials such as diamond, graphite, ceramics are examples of crystalline solids. Here, the term anisotropy means the property of crystalline solid to change the value of physical property when measured along different directions. Here some important notes about crystalline solid. A single crystal has an ordered arrangement of constituent particles throughout its bulk. Majority of crystalline solids, including metals, are polycrystalline in nature. Single granule of polycrystalline solid is made up of many single crystals or crystallites packed together with different orientations. Single crystals are difficult to obtain. Diamond is an example of naturally formed single crystal. Next to this, we will see the second type of solid, that is amorphous solid. The particles of a liquid are in a constant motion. The stop action photograph of a liquid describes the amorphous state. In fact, they are supercooled liquid, that is, they also called as pseudo-solids. Amorphous solids have the following characteristics. First one, the constituent particles in amorphous solids are randomly arranged. The particles do not have long-range ordered structure, but they do have a short-range order. Second, amorphous solids do not have sharp melting points. They melt gradually over a temperature intervals. On heating, amorphous solids gradually and continuously soften and start to flow like liquids. Third one, these solids are isotropic. In other words, their properties such as refractive index, conductivity are all independent of direction of measurement. They exhibit the same magnitude for any property in every direction. For example, glass, plastic, rubber, tar and metallic glass, that is metal metalloid alloy, are few examples of amorphous solid. From picture A and B, it is clearly observed the arrangement of constituent particles for crystalline solid and amorphous solid. Next topic is isomorphism and polymorphism. Similarity or dissimilarity in crystal structure of different solids is described as isomorphism and polymorphism. First, we will see isomorphism. Two or more substances having the same crystal structure are said to be isomorphous. In these substances, the chemical composition has the same atomic ratio. For example, NaF and MgO, NaNO3 and CaCO3 are isomorphous pairs and have the same atomic ratios, that is 1:1 and 1:1:3 respectively of the constituent atoms. Next to this, polymorphism, a single substance that exists in two or more forms of crystalline structure is said to be polymorphous. Polymorphs of a substance are formed under different conditions. For example, calcite and aragonite are two forms of calcium carbonate. Alpha quartz, beta quartz, and cristobalite are three of the several forms of the silica. Polymorphism occurring in elements is called allotropy. For example, three polymorphic or allotropic forms of carbon are diamond, graphite, and fullerenes. Now, classification of crystalline solids. Crystalline solids are further classified into four categories: ionic solids, covalent network solids, molecular solids, and metallic solids. First, ionic crystals. Ionic crystals have the following characteristics. First, the constituent particles of the ionic crystals are charged ions. The cations and anions may differ in size. Second, each ion of the given sign of charge is bonded to ions of opposite charge around it by Coulombic force. In other words, the particles of ionic crystals are held by electrostatic force of attraction between oppositely charged ions. Third, ionic crystals are hard and brittle. They have high melting points. Fourth, these are non-conductors of electricity in solid state. However, they are good conductors when melted or dissolved in water. For example, NaCl, K2SO4, CaF2, KCl are ionic crystals. Second, covalent network crystals. Characteristics of covalent network crystals are as follows. First, the constituent particles in a covalent network solids are atoms. Second, the atoms in these crystals are linked by a continuous system of covalent bonds. The result is a rigid three-dimensional network that forms a giant molecule. The entire crystal is a single molecule. Third, as a result of rigid and strongly bonded structure, covalent network crystals are very hard. In fact, they are the hardest and most incompressible of all the materials. These crystals have high melting and boiling points. Fourth, the electrons are localized in covalent bonds and hence are not mobile. As a result, covalent solids are poor conductors of heat and electricity. For example, diamond, quartz, that is SiO2, boron, nitride, carborundum are covalent network solids. Some important facts about covalent network solids. First, diamond is the hardest known material. Second, graphite is a covalent solid, it's soft and good conductor of electricity. Third, both ionic and covalent crystals are hard and have high melting and boiling points. We can use electrical properties to distinguish between them. Both are insulators at low temperature. Fourth, ionic solids becomes good conductors only at high temperature above their melting points. Fifth, the conductivity of covalent solids is in general low and increases with temperature. However, there is no abrupt rise in conductivity when substance is melted. Third, molecular crystals. Substances such as Cl2, CH4, H2, CO2, O2 on solidification give molecular crystals. Crystalline organic compounds are also molecular solids. First, the constituent particles of molecular solids are molecules or unbonded single atoms of the same substances. Second, the bonds within the molecules are covalent. The molecules are held together by various intermolecular forces of attraction. For example, A. Weak dipole-dipole interaction in polar molecules such as solid HCl, H2O, SO2 which possess permanent dipole moment. B. Very weak dispersion or London forces in non-polar molecules such as solid CH4, H. These forces are also involved in monoatomic solids like argon, neon. These substances are usually gases at room temperature. C. Intermolecular hydrogen bonds in solids such as H2O, that is ice, NH3, HF, and so forth. Third, because of weak intermolecular attractive forces, Molecular solids are usually soft substances with low melting points. Fourth one, these solids are poor electrical conductors and are good insulators. Fourth type of crystalline solid is metallic crystals. These are crystalline solids formed by atoms of the same metallic elements held together by a metallic bond. Metallic bond. In a solid metal, the valence electrons are delocalized over the entire crystal, leaving behind positively charged metal ions. Therefore, metal crystals are often described as an array of positive ions immersed in a sea of mobile electrons. The attractive interaction between cations and mobile electrons constitute the metallic bonds. Important notes about metallic solids. Metallic crystals have the following properties. First, metals are malleable, that is, they can be hammered into thin sheets. Second, metals are ductile, that is, they can be drawn into wires. Third, metals have good electrical and thermal conductivity. For examples, metals such as sodium, potassium, calcium, lithium, iron, Orium, silver,